All right, so these notes are for section 4 of chapter 7 in chemistry. Your objectives in this section are to define an empirical formula and explain how the term applies to ionic molecular compounds, determine an empirical formula from either a percentage or mass composition, explain the relationship between empirical formulas and molecular formulas, and then determine the molecular formula from an empirical formula. So that's a jumble of words, but essentially you get this idea of an empirical formula and you use it a lot of different ways. So an empirical formula shows the smallest whole number ratio of elements in a compound, but smallest whole number ratio means like it's reduced. Not all formulas can or should be reduced. So that's why when it talked about molecular formula, it's different than an empirical formula. An empirical formula is the formula for an ionic compound because they're always reduced. But molecular formulas may or may not be reduced. That's what you're trying to figure out, ultimately. But the first two examples that we did in class yesterday, so if you've done this already, you can actually skip on to the next thing, next video. But just in case you weren't here, I have these two examples to go through. So the main idea is you have these machines that you can stick a substance into and it'll spit out, it'll tell you that it's 36.70% potassium, that's 33.27% chlorine, that's 30.03% oxygen. So the machine will tell you that information. But otherwise, the sample that you put in is some size. Who cares what size it is? It could be 6 grams, it could be 16 grams, it could be whatever you want it to be. But we actually want it to be a 100-gram sample because then we can start working with our masses for individual elements. So we're going to assume that it was a 100-gram sample because then I know that 36.70 grams of that was potassium. So if you see percents, just assume it's a gram. Makes it easy. And then you start to turn those gram amounts into moles. Potassium on your periodic table is 39.10 grams per mole. So I divide those two things, I get an answer, which happens to be 0.9386 for this first one. And then I'm going to do the same thing for my other two elements. I got 33.27%, just change it to a gram chlorine. And then I divide by 35.45 grams per mole, because that's chlorine's mass in my periodic table. And I'll get an answer that, that looks kind of familiar, 9385. Very, very similar to that first answer. And then I take my 30.03 grams for oxygen. I divide by 16.00 grams per mole. And I get an answer that's more like 1.877, right? So that takes me to my next step. And my next step is just to do a ratio of all these mole amounts that I came up with, right? So these all could have a label. So when I said mole ratio before, that's where that comes from. So I'm going to divide by the smallest in all cases. So this first one, I'm going to take it and divide it by 9385. And I'm going to get something that's really, really close to 1. It'd be like 1.0001. So in all reality, it is a 1. That's the point of this, is that I get this whole number ratio. So if you get something that's very, very close to a whole number, that's just your answer. This next one, it's going to be exactly 1 because I'm dividing it by itself. So I know those two things are 1s, but when I divide 1.877 by 0.9385, that's going to give me 2, right? And in this case, it's going to give me exactly 2. But it doesn't always have to be exact. Sometimes it's like 1.9998. Sometimes it's 2.001, right? But the whole number ratio that I got here tells me what my formula is. So I'm going to have 1 potassium, 1 chlorine, and 2 oxygens in this compound. That is my formula. that is a real thing. It's called potassium hypochlorite. But again, you didn't have to memorize chlorite. So hypochlorite or chlorite or hyperchlorite, or excuse me, chlorate and hyperchlorate. So like you might not know that that's a real thing, but it is a real thing. So this is a valid answer. So a lot of the answers you get will be things you recognize, like it could have been a potassium sulfate instead, right? So you'll know most of the answers make sense because you'll see something that you've seen before. So then the next example, I'm going to do the same thing. It's actually 17.15 grams that I'm going to turn into moles. Carbon is 12.01 grams per mole, right? Then I'm going to do the same thing with the hydrogen, 1.44 grams of hydrogen divided by 1.01 grams per mole. And then I'll take the 81.41 grams of fluorine and I'll divide that, I think it's 19 for fluorine on the periodic table. And I'll get three answers here. And these are not nice answers. They're never going to be nice answers initially. So for 1.428, 1.426, and then 4.285. But two of those things are very similar. So again, when I divide the 1.428 by 1.426, I'm going to get 1. It's going to be close enough to 1 that you can just round it to 1, right? This is exactly 1. This last one, though, when I divide it, is going to give me a 3.005, which again, that's really, really close to 3, so that's what the answer is. I don't have to, I'm looking for whole numbers. It's only when it's not close to being a whole number that you have to worry. So I'd have 1 carbon, 1 hydrogen, 3 fluorines. That's a real possible compound because carbon likes to make 4 bonds. This would just be 3 fluorines, 1 hydrogen. We might have done that before as an example because it would be polar because they don't cancel in that tetrahedral when those fluorines pull way harder than that hydrogen ever could, right? So maybe we've done something like that before. All right, so the rest of the examples are in a different video. So